Welcome back, folks. So today we're going to look at another in our series of transistor projects. In this case, we're going to look at a Class A transistor amplifier. Now, I can't go into all the details about how you figure out the bias and configure your amplifier for the appropriate gain and everything else. That's about 3 chapters, sometimes 4 chapters in all the textbooks that I have. So what I can do here is go by some rules of thumb and discuss some of the choices that I've made here. Before we get into that too much, let's pop over and get a word from our sponsor for this project, PCBWay. PCBWay is a fantastic place to go and get your prototype PC boards made up. They make it so simple, they do it so quickly, and they just do it with extremely high quality. But once your prototype has been designed and finalized and you want a custom case for it, where do you go for that? Well, PCBWay. They have complete sheet metal fabrication service, and they explain their process. They tell you what the capabilities are, what their sheet metal cutting types are, even give you the advantages and disadvantages. And they have a vast array of fabrication processes, materials, surface finishes, colors, anodization, powder coating. So you need a special case built up. It's just as easy as it is getting PCB boards made. You get a quote from them. All you have to do is put your CAD files in place, tell them how many they want. It'll decide the design units from the CAD files you put in, but you can also put all this stuff in manually. Select your materials, select your colors, and submit your information, and they'll come back to you with a quote for what it's going to cost. It's just that easy. Anything you do at PCBWay is done easily, it's done quickly, and it's done right. Give them a try. Right. So here we are. This is a schematic I've come up with. So let's look at some rules of thumb here. So this is the 1/10th rule. And the 1/10th rule states that your voltage on your emitter should be about 1/10 your supply voltage. So here we have a supply voltage of 10 volts. So we're looking for maybe about 0.1 volts between the emitter and ground. And that's on DC. Things are very different on the AC side of things. But first we're going to figure out the DC biasing of the transistor. So we want to get the transistor up and running in its most linear mode. And that's usually to set the Q point or where the transistor is biased quiescently to be about 50% along the load line. So we're going to use the 1/10th rule. So we also want volts CE to be about 0.5 of VCC, or around about 5 volts. Now, in order to get that, we'd need collector resistors to be about 4 times the emitter resistance. Now, I've set it up here for a base voltage of about 1.8 volts. You can see that 2.2K divided by 2.2 plus 10K gives us 1.8 volts roughly. So that means our emitter voltage is going to be that 1.8 volts at the base minus the 0.7 volts, which is the voltage drop across the base emitter diode, to give us about 1.1 volts. So that's pretty close to our rule of thumb here. So we want the emitter current to be about 1 milliamp. So we need the resistance on the emitter to be about 1K. And therefore, our collector current is going to be about 4K. And 4K is not a popular resistor value, so I chose 3.6. And I've split this up down here. I'm going to explain that in a minute. But I've got 180 plus 820, which are both common resistor values. And that'll give us our 1K down there. Now, getting into more about why I made some of these choices here. The absolute value of gain is equal to the collector resistance. And this is the AC collector resistance. But since we don't have any capacitors up here, it's going to be the same as the DC resistance, divided by the AC emitter resistance and the AC intrinsic emitter resistance. And what I mean by that is the voltage resistance seen across the base emitter diode. And that's something that is calculated out on the physics of silicon transistors. And it works out to be 25 millivolts divided by the DC emitter current. So in our case, that is 25 divided by 1.1, or 22.7 ohms. So now we can use that in this formula here to look at some of the gains we're going to get here and what these different things mean here, why I have all this. So in bypass mode, this 100 UF capacitor here is going to be coupled across both of these resistors. So basically, as far as AC signals are concerned, it's going to be a direct short to ground. So this point here will become an AC ground. It's not going to be a DC ground. You'll still measure 1.1 volts DC at this point, but you'll measure 0 volts AC. And what does that do to the gain? Well, then we only have intrinsic base emitter resistance. So we have 3.6K divided by 2.7 ohms. So we'd have a gain of about 159. And now I have this thing here called swamp. Well, what's that? So this is a little bit tougher to explain. When you load the emitter down with resistance that could be seen by the AC, if it's significantly higher than the intrinsic resistance of the emitter, what you'll have is you'll sort of couple the base voltage and the emitter voltage together. And it used to be called bootstrapping. I don't know what people call it these days. But so they're bootstrapped together. Whatever happens here at this point, you're going to find that the emitter voltage will be about 0.7 volts less than this. Whereas in the case where it's bypassed, this is at 0 volts AC. So what will that do? It just means that, as the base voltage goes up and the current through the emitter increases, the emitter voltage also goes up a bit. That will reduce the current flowing between the base and the emitter. And I'm talking here again about AC current, not DC current. So it tend to reduce the gain. Now, if you look at the gain curve of a typical transistor, it kind of goes up like this. And we kind of want to be in this region here. So as it goes up like this, the gain increases dramatically as the base current goes up. You tend to get a little bit of distortion. Basically, what the swamp mode is doing is kind of giving a little bit of negative feedback to the circuit, which reduces that distortion. But what you're going to do is you're going to sacrifice gain. So in swamp mode, you have 3.6 divided by 202.7 ohms. In other words, the 180 plus the 22.7 in the emitter. And that'll give us a gain of around 18. So in order to get that low distortion, you're going to have to give up the gain. Now, if you really wanted to get a lot of gain, you could put two of these stages together so that you're still going to get 18 times 18, which is a gain of 324, which is considerably more than this, but you'll have a lower distortion circuit at the cost of a little bit more circuitry. So let's go to the open option here. So open option is both of these jumpers are off, and the emitter sees not only its internal resistance, but it's also going to see the full resistance of this 180 and this 820 together. So you'll have a total AC resistance of 1022.7 ohms, and that reduced the gain down to 3.5. But anyway, so what we're going to do, we're going to build up this circuit and we're going to try it out. Now I've put test points on the circuit at the collector, at the base, at the emitter, right at the emitter, and down here after the swamp resistor. And we're going to have a look at the signals at all those areas. All right, let's see what kind of a layout I came up with for this. So as usual, what I did is I tried to put all the traces, connecting everything on one side. And if you go to the bottom, I've got that as a ground plane. Again, it won't be necessary in this circuit. I mean, we're not really building a truly hi-fi amplifier. But like I said before, it's a good habit to get into just in case you do decide that someday you've got the skills to design a really, really high-end amplifier. You're going to want that ground plane there to reduce noise. So what I've done here is I've laid it out pretty much the way we saw in the schematic. So if you look at that, we have our collector and emitter resistors down here, all in line with the transistor. And we have our base bias here. And we have these big capacitors. So these big capacitors they're just basically to block any DC. They're just AC coupling. And I've made them big enough that this thing should be able to work, given the impedances of it going in and out, should be able to work at all audio frequencies. And we could check that out when we get the thing in. As soon as the board gets in, we'll build up a couple of these and try them out. If you do decide to do something like this, you could play around a little bit, but I would look to get yourself a textbook. Like I said, the ideas I've used behind here are all just kind of rules of thumb. You need to know really where all those rules of thumb come from, and that's kind of beyond the scope of these little videos that I'm doing. Like I say, it could be 2 or 3 chapters just dealing with basic Class A type amplifiers or common emitter amplifiers. Let me go back over here. So if we look at a Class A amplifier, it's a common emitter. So the emitter eventually goes down to ground, especially in the bypass mode. It's AC. The emitter is grounded for AC. And it's Class A because it's conducting all the time. So regardless of what's happening here, there's going to be DC current flowing down through here. And the AC current will be added to that. So it'll take the overall current up and down. All right, guys. So I'll come back to this again when we get the boards in from PCBWay. And we'll see you in the next one. Thanks a lot.